In this section, we're going to start taking a look at more trigonometric formulas and identities. And so the three that we're going to focus on are going to be our double angle formulas, our power reducing formulas, and our half angle formulas. We're going to start this video by looking at double angle formulas. And so these are the double angle formulas that we should know. All right, we don't have to memorize these, but we should at least know how to work with these. All right. And I'm going to start this video by proving the one of the easier ones, the sine of 2x equals 2 sine x cos x. Okay, so if I wanted to prove that the sine of 2x is equal to this 2 sine x cos x, we could rewrite sine of 2x as sine of x plus x. And the reason I would want to do that is because then what I could do is I could use one of the sum and difference formulas that we looked at in the last video series, okay? And by the way, this is how you can prove any of these formulas, right? Now remember, sine of x plus y, if we look at our identities, sine of x plus y is sine cos plus cos sine. But in this case, x is x and also y is x. And so what we end up getting is we end up getting sine of x cos of x plus cos of x sine of x. And clearly, these are like terms, and so that turns into 2 sine x cos x. Okay, so that's literally how easy it is to prove the double angle formula for the sine. Okay, if I wanted to prove the cosine of 2x, I could do it the exact same way. I could write cos of 2x as cos of x plus x. Okay. And if we use our formula, okay, so let's take a look at our formula for our cosine. So cos of x plus x, or x plus y in this case, is cos cos minus sine sine, okay? So this is going to be cos x minus sine x sine x, all right? Or I could write that as cos square x minus sine square x. Now that is not 1. That's cos square x minus sine square, all right? And so actually that's this formula right here. If we wanted to show the others, we could use the Pythagorean theorem, or the Pythagorean identity, excuse me. So for instance, remember that cos square is the same thing as 1 minus sine square of x, and then we have this minus sine square of x, and so that would be 1 minus 2 sine square of x. Okay, so that's how we derive that part of the formula right here. All right, and of course we could do the exact same thing with the sine function. Okay, so if I wanted to prove the third, what I could do is I could take that statement, that cos square minus sine square, and instead I could rewrite this as cos square x minus 1 minus sine square of x, right? Just by changing this sine square. So I'm just taking this statement, moving it down here. That's the sine square. This would be cos square of x minus 1 plus, and by the way, this should be a cos square. If I'm proving this, sorry about that. Okay, and then this would be a cos square of x, right? And then finally, this would be 2 cos square x minus 1, which is the third formula, okay? So that's just going through and proving some of those double angle formulas. So let's just assume that we proved all of them, okay? This one, we could just take the ratio and do that pretty easily. So now let's go through and take a look at some of our applications of this. So given the following triangle, okay, we want to try to find the exact values of sine 2x, cos 2x, and tan 2x. All right, so what will probably be helpful for us is to identify that in this triangle, the sine of x is the opposite over the hypotenuse, which is 12/13. The cos of x is going to be equal to 5/13 adjacent over hypotenuse, and the tangent of x is going to be the opposite over the hypotenuse, which is 12/5. Sine of 2x is 2 sine x cos x, or that's going to be 2 times the quantity of 12/13 times 5/13. And then finally, 2 times 12 is 24. 24 times 5 is 120. We get 120 divided by 13 times 13 is 169. Okay? So that's literally how easy it is to employ these double angle formulas. Okay? For letter B, if I want to try to find the cos of 2x, I could use any of the formulas. Okay, so remember, cosine has three variations of this. Now I'm just going to use the cos square minus sine square. Okay, and I'll show you guys why. If I use either of the two with the ones in it, I'd have to get a common denominator. Okay, this avoids me having to get a common denominator. Okay? So this is the same thing if I want the cos of 2x. That's the same as cos square x minus sine square of x. Or that's the same thing as 5/13 squared minus 12/13 squared. And if I square that out, that's going to be 25 over 169 minus 144 over 169, right? And 25 minus 144, that's going to give me negative 119 divided by 169, all right? So that's all we have to do with that. Okay, not meant to be too tough. The other way, we'd have to get a common denominator, okay, and it might be a little bit messier. Right? Last one we have is the tangent of 2x. And the tangent of 2x is going to be equal to, we have our formula up here. So that's 2 tan of x, 1 minus tan square of x. Okay, so in our 2 tan of x, 1 minus tan square of x. Okay, we know that the tangent is 12/5. Okay, so that's going to be 2 times 12/5 divided by 1 minus 12/5 squared. All right, so unfortunately, we got a little bit of algebra to do here. Not that big a deal. Okay, 2 times 12/5, that's going to end up being 24/5. Okay. In the denominator, we have 1 minus 144 over 25. Right? And then we can rewrite this as 25 over 25 minus 144 over 25, which is precisely what we just did right here. So that's negative 119 over 25 for your denominator. And then finally, we can multiply by the reciprocal to clean that up. So 24/5 times a negative 25 over 119. That's going to simplify. That's going to become a 5. Okay. And then this is going to cancel out. 24 times 5, we should have negative 120 over 119. Okay. All right. So that's all we have to do with these. Okay. Just employing our formulas and then just doing some computation. Okay. I'd also urge you to use your calculator to be able to verify this as well. Shouldn't be that difficult as long as you use your parentheses correctly to put that in. Okay. All right, so in the next video, we're going to take a look at a couple more examples of how we can use the double angle formulas.